Okay. Hi, how are you? So we're going to continue on through Unit 3, and we're going to change pages. We're going to talk about gases. Now, we did 3.1, which was intermolecular forces. Remember, Unit 3 is a whopping 20% of the AP exam. That's a fifth of the exam. So it starts with your intermolecular forces, and that is your solids and your liquids, because gases are assumed to not experience intermolecular forces of attraction between one gas particle and another gas particle because they're so far apart that there are no forces of attraction. Now, that is an assumption, and in a few lessons, we'll talk about that assumption, okay? And we'll elaborate on that, but that's not the purpose right now. So the purpose right now is just to get into our basic gas law variables and how they relate to each other. And there'll be a few maybe new things. I really would like to say to you, gas laws are deceivingly easy. They appear so easy when you're learning them, but the application through problems, I find to be some of the more challenging questions, and I experience that with students often as well. Okay, so don't get complacent, and just stay diligent, as many of you have been wonderful about that. Okay, so don't get complacent. They are deceivingly easy. All right. So I'm going to go ahead and get started. I'm going to break this up into a few different, I'm trying to get my screen up. It keeps giving me a hard time. I'm going to try to break this up into smaller chunks. I'll probably ask y'all's opinion about that in class. So today, I'm about to get there, is your basic gas laws. All right. I don't want red. I like the darker. I like dark blues and stuff. Gas laws. All right. So we talk about gases. They're far apart. They don't experience forces of attraction. Easily compressible. We can take a large volume and push it into a small volume because there's so much space in between the particles. We can get rid of that space and compress gases. Now, we will talk about pressures. You need to be able to describe what causes the pressure of a gas, all right? So it is caused by the collision of, I'm going to say, gaseous molecules. It could be a liquid. You could talk about liquid pressure, I guess, caused by the collision of gaseous molecules with the side of the container that it's enclosed in, right? So, if you want to envision, you got these gas particles. They fly around. So listen to me, in random motion, right? And they collide with each other. They collide with the walls of the container. And those collisions cause the pressure. It is a force, okay? Pressure is a force of pressure, all right? So the greater the force they're colliding with, the walls, the greater that pressure is going to be. Now, we will measure pressure in one of several different units. So units of pressure. Well, let's see. We've got atmospheres. We've got millimeters mercury. Let me go ahead and ATM is for atmospheres. So you'd say 1 atmosphere pressure, 2 atmosphere pressure. I'm going to get rid of that S. Okay. mmHg is literally a measurement of the millimeters of mercury, right? Hg is the symbol for mercury. And they would set up There's something called a mercury. Well, that's a thermometer. That's different. Well, there's mercury. I totally just lost the name of it. Oh, a manometer, a barometer, a manometer, a manometer. It'll measure pressure. Maybe it's a barometer. I don't know. It's been a long day. I say that in every lesson. We've got Tor, named after a scientist, Torricelli. He studied pressure. And we've got kilo. Well, let me keep my same trend. Let me give the symbol here, kilo, and this is kilo pascals. Oh, I need to write that. It's called torr. It's called torr. It's the same thing. All right. All of these are units of pressure, just like degrees Celsius, Fahrenheit, and kelvins are units of temperature. These are different units of pressure. Now, let's look at how they are related. 1 atmosphere is equal to 760 millimeters mercury. 1 atmosphere is also equal to 760 torr. What that means is that torr, and millimeters mercury are the same. So 700 millimeters mercury is equivalent to 760 torr. They're identical. You can just interchange them. All right. And then 1 atmosphere is equal to 101.3 kilopascals. You're probably not going to see kilopascals. You're much more likely to see the millimeters mercury and the atmosphere. But if you do, you'll see it there. So if you need to convert your units of pressure, those would be your conversion factors. All right. So when we talk about gases, pressure is always a factor. Another unit that's always a factor is going to be our temperature. All right. The temperature variable, not a unit, the variable of what is the temperature will also be a factor when we talk about gases. And, you know, we can have degrees Celsius and we can have kelvins. If you don't recall, Kelvin equals degrees Celsius plus 273. And sometimes people write 273.15. It shouldn't be an issue. Okay, so whenever you use temp, the Kelvin temp, I'm gonna write the, must always be used, always be used, always be used when plugging temp into an equation. All right, I say it, it's easy. It's also easy to forget because I see students do it all the time. You cannot plug your Celsius temperature in and solve the problem. You will get the wrong answer. You can't plug in Celsius, solve the problem, and then somehow magically convert it to kelvins, because that wouldn't even make sense. You must convert any temperature value to kelvins. As soon as you get it, turn it into kelvins. Okay. Unless you need to change in temperature, then it doesn't matter. Okay, that's our temperature. Okay, we also have our volume. And your volume, there's not much to say about that. It's in liters for the most part. And we have our number, excuse me, I'm stiffling, you guys. I apologize, but I kind of feel like I'm getting sick, and you're not allowed to get sick during COVID, but I'm so quarantined. Number of moles of gas, I'll just write that, is N. All right. So this unit will have a lot, well, this part of this unit will have to do with we have the solids, the liquids with intermolecular forces, gases here. We'll talk about solutions and then some new things with solutions, some types of laboratory techniques. So, but when we talk about gases, so this part of this unit, we'll definitely talk a lot about pressure. Pay attention to the units, temperature, pay attention to the units, volume, and the number of moles of a gas. All right. And let's go ahead and write this out, that at STP, remember STP is standard temp and, pressure. So what is standard temp? It is 0 degrees Celsius, and it is a pressure of 1 atmosphere. At these conditions, we know that 1 mole of any gas, doesn't matter if it's a big heavy gas like carbon dioxide or a light gas like hydrogen, we will have this many particles. Oh my gosh. Yeah, I meant to write the volume. I was just thinking mole. We'll have a volume, I'm sorry guys, of 22.4 liters. Okay, so we call this the molar volume of a gas. I have a funny story I could tell you about that if you remind me. It's kind of funny. If you remind me, okay. 1 mole of any gas, but the conditions have to be as such, okay? If the conditions are not as such, then it's no longer the case. This is not true. It's only true with this temperature pressure. So what we see, what you should recognize here, is that the temperature, the pressure, the volume, and then of course the number of moles would be kind of on its own, but they're all related, okay? So this equals this when this is this. And we can adjust any one of those. And that's where your gas laws come in. Okay, so let's get to the gas laws. If you guys that were in my class last year, if you remember my story, I'm trying to remember the difference between Charles and Gay-Lussac's. And those of you that remember my story, I have a friend who's gay. His name is JP. So this is pressure and temperature. So Gay-Lussac's law. Okay, and I can never remember which 2 variables. I now know that it is pressure and temp. Okay, and in class we will look at a demo, a visual of this, a great gas visual. And we know that, think about it, right? I'm going to create your visual before we look at it in class. If I have my gas particles in here and I heat them up, well, what's going to happen? They're going to start moving more quickly, right? And they're going to start banging in the walls with greater force and more often, then harder and faster. So as my temperature goes up, we should see that pressure go up, right? That just makes sense. And you should, somewhat be able to describe it very simply. But that formula is going to be P1 T1. That is not true. P1 over T1 is equal to P2 over T2. Okay? Such that the ones here are your initial conditions. You probably remember this from last year. These are your initial conditions. And the 2's here are your final conditions. And in order to solve this problem, if you are algebraically challenged, it is as simple as cross multiplying and setting them equal to each other. So essentially you multiply and divide, right? If you have questions about that, let me know. And then the only other thing is to keep in mind that the temperature must be in kelvins. And I say it, and then some students just invariably forget. And even, some AP students, I'm like, hey, man, your temperature's in Celsius. You can't do that. So you can't do that. And that is our first gas law that we see. It is Gay-Lussac's law, and it's going to relate our pressure with our temperature. We have a direct relationship, okay? Of course, we are assuming here that the volume, the other variable, and the number of moles is unchanging. right? Because they're not present. Okay, let's see, that could take me to another gas law, which is Charles's law. And that's going to be, it's going to relate our volume and our temp with the knowing that the number of moles and the pressure is constant. And to think that that pressure is constant is the way to understand this, because if our temperature goes up, right, we just said that pressure should go up, right? Well, but in Charles's law, the pressure is constant. So in order to account for that, we have an expanding volume, right? And that allows that pressure, it allows it to kind of absorb that pressure, and you don't get the buildup of the force because the size of the container just gets bigger, right? So it minimizes the change in temperature. And we've got, once again, a direct relationship here where one goes up, the other goes up, one goes down, the other goes down. So we'll see the same equation. We just substitute V for, oops, so let me substitute V for T. V for P. We substituted volume for pressure. Once again, these are the initial conditions, right? And these are the final conditions. And you must, as always, put your temp in kelvins, right? Kelvins is the lowest possible temperature is kelvins, is 0 kelvins. So that doesn't allow you to ever have a negative Kelvin temperature. And that's why we have to use kelvins, because imagine if my temperature here was in Celsius and it became negative, then I end up with a negative volume when I do the math. And that's illogical to have a negative volume. So you always have to use kelvins. You'll never end up with negative values that don't make sense. And once again, I apologize. We would just cross multiply, okay? And just to give you a hint, you know, it's basically this times this, the two givens divided by the guy who's, divided by the guy who's with the unknown, right? So you multiply the two that are given and you divide by the unknown, and you're gonna get that guy there. Next law is the one I usually start with, most people do, is Boyle's law, right? And Boyle is going to relate pressure and volume. Boyle's one of the first scientists to do labs and collect data and analyze data. I think there's something true about that. And to run multiple experiments and to really start looking at the connections between values and variables. Okay, this is going to be P1, V1 equals P2, V2. All right, we're going to have an indirect relationship. Once again, the ones are the initial, the twos are the final. Really doesn't matter as long as you have the correct pressure with the correct volume together. And let's see, right, if the pressure goes up, because this is an indirect, well, let's look at it in terms of volume. If the volume goes down, right, if we have this amount of space to this amount of space, but we have the same amount of particles, 2, 3, 4, 1, 2, 3, 4, you can see that the smaller the volume, the greater, the more collisions you're going to have with the walls of that container. And the more collisions you have, the greater that pressure is, the more force you have. So this is going to have a greater pressure due to the smaller volume. And that is an indirect relationship, right? As one goes up, the other goes down. And here we have a lesser pressure due to the greater volume, that greater volume allowing for less collisions with the wall, therefore less pressure. Okay. Now, Those are good. And I am not going to go through an example of every one of those, okay? You can plug in numbers and solve for the unknown variable. You can figure out which formula, excuse me, do I need by just looking at the information that is given to you. You should have that skill, okay? And if you don't, you can ask me for help and I will not judge you. But you've got those three formulas. I will give you a hint, okay? The last formula was Boyle's law, right? And that looked, oops, I'm sorry, guys. That looked like this, okay? So if you can remember that P and V are always on top, you can put T on bottom, okay? If the volume is not changing, then I can just use this formula. P over T equals P over T. And I can ignore the volume. I can just totally ignore it. So you can memorize that. P and V are on top, and sorry, temperature is on bottom. The other way to look at this is like this. If the temperature is not changing, okay, so temperature is not a factor, then P and V are always on top, right? P and V are always on top. If the pressure is not changing, but the volume is changing, then we can just look at this in terms of our volume. V over T equals V over T. If for some reason you needed the number of moles to fit in here, it would go on the bottom, right? What I had right here is actually called the combined gas law. And it combines all three. Get rid of what you don't need. If you don't need temperature, ignore the temperature, and that's your equation, right? If you don't need the volume, then ignore the volume, and that's your equation, etc. And like I just said, you can always put moles on the bottom, and that would work as well, okay? Now, those are your gas laws. These are these laws are used when your conditions are changing. And we know that because we've got an initial set of conditions and we've got a final set of conditions. If conditions are not changing, but we are at a particular state, then we need another equation, right? And that is our wonderful ideal gas law. Ideal gas law. And this is an equation of state, unlike the others, right? This gas law is used when we do not have a set of changing conditions. This is at a moment in time, right? At this moment in time, when the temperature is this, the volume is this, the pressure is this, what moles would we have? We have this many moles at this volume and this temperature, what will the pressure be, right? So at a moment of time. And you'll know because you'll be given, you won't have two pressures, you won't have two of anything. Our ideal gas law is PV equals nRT, and Miss Murphy famously calls it the pervert equation. Kind of looks like pervert, all right? But I've changed it to PIV-NERT, is the PIV-NERT equation. Obviously, this is my pressure, this is my volume. In order to use this equation, my volume must be in liters. All right? Now, pressure, it can be atmospheres, it can be millimeters mercury, which is the same as torr. It can be kPa. Oh my gosh, I don't know if I remember my R values from, okay, we'll get to it. Volume is in liters. N is number of moles of gas. All right. R is the universal gas constant. Now listen, guys, during the course of this class, we will see that there are a few different R values, not just here. We're going to look at about 3 right now. I hope I can remember what they are. There's going to be an R value. There's different units for R values. So this R is a gas constant. So there must be a unit of pressure in it. I'm just going to leave it at that. Okay. And the value is dependent upon the unit of pressure. I don't know. I know that Miss Murphy's class last year, we were in the middle of our gas unit when COVID hit. All right. So, and I'm not sure about the other ones. Miss Van Pelt may have been a little in front of me. And then T is your temperature. It must be in kelvins. And I don't know where Miss Ross or Mr. Sunpearl would have been. Just throw that out there. Okay. Okay. So R, we need to talk more about R because everything is easy. Okay. Plug in your pressure, plug in your volume, make sure it's in liters, plug in or solve for N, same with pressure, plug in or solve for T. Now your R value changes. All right. The R value is a constant that changes quite often. Not really. There's just only a couple different R's we will be concerned with, okay? So R is dependent on their unit of pressure. If pressure is measured in atmospheres, R equals 0.08206 L liters, atmospheres, moles, Kelvin, okay? If the pressure is measured in atmospheres, then this is what R is equal to. If the pressure is measured in millimeters mercury or torr, then R is going to be equal to 62.4 liters mmHg moles kelvins, or liters torr moles kelvins. If pressure is in kilopascals, we have 8.31 liters, kilopascals, moles, kelvins. Now, obviously, I've memorized them. I've been doing this for a long time. What I would recommend to you, you will be provided these R values on your equations and constant sheet, but you don't want to be wasting your time looking for constants. So what I often suggest is memorize this one because it's the most common one in this course. And you could easily convert your pressure to atmospheres. You're probably not going to see kilopascals, guys. You could easily convert your pressures to atmospheres by, let's see, dividing, if you have millimeters mercury torr, just divide by 760. And you can memorize one R value and just convert your pressure to atmospheres and use that R value. Anyway, so it's all good, right? It's all good. We just plug in, as you know, our unit of pressure, or we solve for it. We plug in or solve for volume. It must be in liters because of the liters that are down here in these units. Okay, so in order for our units to cancel properly, we must have liters. We have our number of moles of gas, which you see right here, right? We have our temperature here, and you'll see that down here. It's kelvins, right? Now it just occurred to me, because we're about done here. I'm not going to go through a bunch of examples. I think you can determine what is your equation to use. But I would like to say, it just occurred to me that when it comes to temperature, and we'll see this in another part of the course, yes, you must plug in a Kelvin temperature. Never mind, it doesn't pertain. Never mind, they don't need to do it, sorry. Sorry. I'm going to leave that at that. Those, no, I'm not. I'm sorry. Those are your gas laws. There is one more oh so important law. I'm sorry. We need to look at mole fraction. Okay. I know you've seen it. This is where it's most important, in my opinion, is in the gas section. Mole fraction equals of A equals moles of A over moles total. All right. So we'd be talking about a bunch of gases, right? I could have a mole fraction of B equals moles of B over moles total. It's basically getting the percent, the piece divided by the whole, but not multiplying it by 100. All right. So that's the mole fraction of A. This would be mole fraction B. And if there were only two substances, then the mole fraction, I'll go ahead and write it, A plus the mole fraction B would equal 1. Just like if we multiplied it by 100, we would have percentages. Let me clean that up. And it would equal 100. Okay? That's important because the mole fraction of A is also equal to the partial pressure of A over the total pressure. I feel like I should have saved this. Okay? Mole fraction, total pressure, and partial pressure gas A. Okay? I'm definitely going to do some examples. We will definitely do some work on this. This is really, really important that you remember that you have this at your fingertips. Sometimes it's the only way out of a problem, because what this means is the number of moles, all right? Number of moles, gas, and pressure, gas is directly related, all right? One doubles, the other doubles. Well, the moles have to double, right? They can't double. If you double the pressure, then the moles must have doubled. Volume and temperature left behind. But this is important. So if we know the number of moles of each gas, we can, and the total pressure, we can determine the pressure of each individual gas. And the last thing, I promise, it relates to Dalton's law of partial, I've gone too far, pressure, which states that the total pressure is equal to pressure A plus pressure of gas B plus pressure of gas C, ... Okay, I need to stop.